Welcome back. In this video, I wanted to show you how you can optimize the U-slot patch antenna that we designed in the previous video to get some optimum values for these parameters to, let's say, match it over a given bandwidth. So this is also useful for the parametric optimization of inductors and transformers video that I had made. So let's say you have some transformer and you want to get a certain matching network out of it, or you want to get some certain S parameters out of it, or a certain coupling and L1, L2 factors from it. What you can do is you can use optimization like what I will show you in this video to do that. Okay, so what we'll use is not the optimization tool inbuilt in HFSS. I actually don't like that as much. We'll use MATLAB, which is certainly a lot more powerful to control HFSS. Okay, so what you need to do is open MATLAB. So here it is, and I have some codes. We'll go through it one by one. Okay, so the first thing actually that you need to do is before you open MATLAB, go to your system path. So in your settings, go to environment variables, system properties, environment variables, and click on your path, say edit, and make sure you include the location of IronPython that is installed inside your ANSYS EM folder. So find this folder and include it in your path, the IronPython folder, as we'll use Python scripting to do this. Okay. All right. So once you have that included in your path, then what you can do is I'll upload this code onto GitHub so you can download it from there. And you can use the code to basically control HFSS and run any kind of optimization tool. Okay. So let's go through it. I said, okay, make sure you include the system path, and then also make sure there's only one HFSS running when you run this code, because otherwise it might try to open the design file in the wrong application. So just close everything and just keep one of them open. So let's actually do that. So here I have two of them. This is the one we designed, and this other one, which I'm going to close now. Okay, so I've closed that. Okay. So here I'm using an optimization technique called Nelder-Mead optimization. You don't really need to know how it works, but if you're interested, you can look it up. I found it to be very good when you have a few number of variables, for example, like maybe 10, 15 variables or less than that, and you have a very nonlinear optimization function. So let's say you want to optimize the dimensions of an antenna to match it over a certain band. That's quite a nonlinear problem. So Nelder-Mead works very well in such cases. But if you want to use other optimization tools, you can also do that. In this example, I'll show you how to use Nelder-Mead for input matching of an antenna. There are other tools like, you can even use maybe gradient descent if it's a simpler problem, or you could use particle swarm optimization, genetic algorithms, and there are literally hundreds. All of them are implemented in MATLAB one way or another. So I'm just showing you this example, but you can switch it up to use a different one. Okay. So what I have here is parameters. So let me actually open the design file. So we said we're going to optimize over 7 parameters: slot width, slot length, the slot Y location in Y, thickness, patch width, patch length, and the feed. So, just for argument's sake, I'm just going to use the same parameters that I started with here. So let's say, I didn't know what the actual optimum parameters are, and I use these ones: 2.5, 3.5, 1.2. So let's set those: 2.5, 3.5, 1.2, 1, 10, 6.75, and minus 0.75. Okay. 6.75 minus 0.75. Okay, so let's say I started from here, right? So let's run the simulation. Since I don't know what the best values are, this is my starting point. So I'll just simulate it to see what S11 looks like. Right, so these are the parameters, the 7 parameters that I start with. And you need to set some lower and upper bounds, of course. Originally, Nelder-Mead is actually not a bounded optimizer, but there is a bounded version of it, which was implemented and uploaded onto MATLAB's file exchange, which I'll be using. It's called fmin search bound. I'll come to that. So it's kind of like an artificial way of including bounds by making the cost very high when you start reaching the bounds. But anyway, so this is the lower bound for these variables that I've set, and the upper bound, you can obviously change these, but these are what I set them to be. So depending on the variable, you need to set a lower bound and an upper bound. Okay, and then what we do is we run a seed simulation. So this is just simulating the original starting point as a reference. So here I have IP64, which runs IronPython. I have a file, HFSS main, which will generate. And here I'm passing the parameter X, right? So all the variables that I want to change into this file, we'll get to the file, and then I run that command using command line. And this, to run this, basically you need to set the IronPython's file location in your system path. Okay, and then I save S11, and then I read that data and I can plot that data. So how do you generate this file, right? HFSS main. So that's what we'll do. So once this is done, I'll show you how to do that. It should be done in a couple of seconds. Okay, I think it's done now. So there we go. It looks like this, right? So it's sort of matched from 8.5 to 9, but really we want it to be matched from 8.5 to 10.5. And you actually see that the second resonance of the U slot patch is starting to appear somewhere here, but we want to bring it down by optimizing the different dimensions, right? So that you get two resonances that look like this. So to do that, what we can do is first we want to speed up the simulation. So what I'll do is I won't save the fields because I only want to look at S11. And we can simulate from 8 to 12, that's fine. So a lot of the results kind of disappeared, which is fine. Okay. And the next thing I want to do is I will rename this as S-params. You don't have to do that, but I'm just doing it. Okay, so now what we want to do is we want to run a script. We want to save a script. So HFSS has a really useful scripting tool where basically every action that you take will be saved into a Python script. So let's do that. So let's say I say record script to file, and I'll just call it temp script for now. So now everything I do will be saved into a script. So what we should do is change all these variables to some values. 1.1, let's say 1.1, 10.1, 6.65, 0.7. Okay, so those are the 7 variables. And then I'll say validate, close, analyze. So once it's done analyzing, I'll come back. Okay, so it's done optimizing. The next action I want to take is export these results, the S parameter. So right click export, and we'll just save it as sparams.csv. And I also want to clean up solutions. So I'm also, once I export the S parameter files, I delete all solutions. Why do I do this? Because when you're optimizing, it'll run, let's say, 100 iterations. You don't want 100 solutions to be saved on your PC. That takes a lot of memory. So it's better to just delete all the solution or the entire, all the results once you exported the data that you care about. Okay, and then I'm also clearing this, but that doesn't actually get saved. So that's not required. And then I'll go to tools and then say stop script recording. Okay, so let's open that script up and see what it looks like. So go back to MATLAB and then go to temp script. So you see this is the recording that was recorded, the script that was recorded, right? So, it opens ANSYS HFSS, initializes it, opens the project, opens the design file, and then I said, okay, change these properties, right? All of these properties, 1, 2, 3, 4, 5, 6, 7, and then save, analyze, and then get the S parameter report and export it to a file called sparams.csv, and then delete all results. Okay, so now what we need to do is open up this HFSS main script, and all you have to do is these lines, I will copy them and then go back to this temp script and then paste them here. So all this is saying is that, okay, where to look for the Python plugins so that you can run it using MATLAB. Okay. And you also need to have this HFSS script util.py file, which I'll also upload in GitHub. So make sure that is included. And you include these lines in your temp script. Okay. Now what we'll do is we replace these variables with the arguments that you'll pass using the command line. So I'm going to do that. So the first variable is the first argument, second is the second. Let's make this 2, 3, 4, 5, 6, and 7. Okay, that's pretty much it. Um, so I'll also rename this temp script. So I'll call this optem script. Actually, now it's exactly the same as this HFSS main that I had. Right? Except this I had used for the previous designs. So I have these names. But now we are using this because this is what we just made, right? The uslot patch antenna and the uslot patch. So I had used this for a trial run. That's why the names are different. Anyways, the rest of it is the same. So all you need to do is run the script from HFSS, save the script from HFSS, change the variables, and change these first few lines. So then we're pretty much ready. So now what's going to happen? When I, let's also change this to optim script, right? So that's the new script that we made. So now when it runs the script, it'll basically change those 7 variables to what these 7 variables are. And then it'll save the S parameter file as sparams.csv. So since it's going to save it as sparams.csv, we want to read that. So I'll also change this one's name to sparams.csv. Okay. So essentially what we've done so far is we set some parameters and we we run a MATLAB Python script to use those parameters in the HFSS file and then run that file. So let's actually see that in action. Okay, so I'll say clear all, set these parameters, and I run this section. Okay, there you go. So they've all changed. So what was set here. And now it's running the simulation, as you can see. So I'll just give it a few minutes and come back. Okay, so it finished simulating and you can see the results here from this figure plot that I've made here. It's exactly what we saw in HFSS, right? Exactly that. And of course, now the solution is deleted because once the script runs, it also deletes the data. Okay, great. So now we have this. You saw how that works. And now what we need to do is create a function. So the function that I've created is called funcoptimize. Okay, so now what you need to do in this function is you need to take a certain set of variables, in this case param x, and it should return a cost function, a single result, like a single value, which is the cost. And in the optimization, we'll try to minimize this cost, right? So in this case, it's taking param x, which are those 7 variables, and it's returning a cost function. Let's see how I designed it, what kind of cost function that I've created here. So here I'm just printing what the parameter values are. We actually don't need this. And we also need to change this into optim script because that's the new script we created. And one more change we need to make is from S11 to S params, right? So it's the same thing. It runs the script and collects the S parameter data. And I've commented out the figure, but you can also obviously plot the figure each time this optimization runs for each iteration. And then I say, okay, S11 is this S data that we've collected. And I said the cost function is the maximum value of S11 from 51 to 251. So what is that? What is 51 to 251? Let's actually look at that. So if you look at the frequency part of it, so let's say if frequency range is S data 1, right? So if we go open this, so this is the frequency from 8 to 12 gigahertz, 401 points, right? And from 51 to 251 is basically from 8.5 gigahertz all the way to 10.5 gigahertz. So I just want to minimize S11 and I want to match it from 81 to 251 gigahertz, right? And what I'm saying is that the maximum point among all these values, right? So if you plot it, so from 8.5 to 10.5, take the maximum, right? So this is the maximum value around -5 and minimize this. So basically what it's going to try and do is among bit from 8.5 to 10.5, it'll try to minimize the maximum point, right? So if it's matched, then the maximum point should be less than -10, right? And that's how I designed my cost function. For different optimization goals, you need to change the cost function. So in this case, I found this cost function to be the simplest and most effective. The cost function is what defines the linearity and non-linearity of your optimization problem, right? You can make a very complicated cost function. You can do all kinds of tricks here. So this is where optimization becomes difficult or complicated or more interesting, is in designing or defining the right cost function. So for matching, I found this to be a good cost function, so that's what I'm using. And the next thing I do is I save the parameter values and the cost function into a variable, and I write it into an Excel file so that I have a record over the entire optimization, how the optimization has run. And this is just for recording purpose in case you want to go back and look at some results specifically. Since we're deleting all solutions, it's good to have a record of the variables and the results. So that's it, that returns the cost function. So once you have this optimization cost function set up, then what we can do is run this optimization routine. So here I'm using fmin search bound, which is, I didn't write this code. It was written by someone else. So what you can do is just go to Google, enter search for fmin search bound. You can open this file exchange, go to functions. Come on. Go to functions and then you can download this one. But there are other optimization functions as well. There's fmin search con. You can use, like I said, any other function that you like. But all of them require a cost function expression, a cost function setup like this. So I've set the maximum number of iterations to 500, which you can stop midway if you like. And I'm also plotting the cost function output. So this is the actual optimization routine. So this is just syntax, I guess. You send the variable here, the actual function that we've created here, the parameters, the lower bound, upper bound, and the options that we set here. And I'm also recording how much time it took to run this entire optimization routine. Okay, so let me just start running that and show you what that looks like. So let's clear everything, clear this. We're not going to run this again because I already did. Let's run this. Again, it sets these variables to the starting values first, and then runs these results, runs the simulation. And once it creates a couple of results, I'll come back. Okay, it finished one iteration, and you can see that the cost function that it plots here is around -5.06, which is what we saw was the starting point. And then as it will optimize all of these variables. It'll change the first one, second one, third one. It's basically mapping out the canvas or the contour of your cost function by changing one variable at a time. And then it goes and applies the Nelder-Mead optimization. And I urge you to go and look at how that actually works. It's quite interesting. Anyways, this is going to take several hours. So what I'm going to do is I will stop this. Since I already ran it once before, so I'll just show you what the results look like. Okay, so this is what happens after we're done optimizing. So the cost function looks something like this. It took about 6 hours, 6 to 7 hours. And it started here, as we saw. And then if you run it for several hours, it'll just go and optimize all the way to -10.7. And once it does that, you can see that this is what the optimized result looks like, right? So I can also show you the sim history. There we go. It started with these, it changes the first variable, second, third, fourth, fifth, sixth, seventh, and then it starts actually going through and moving around the, it's called the, I don't remember what it's called. It's like an amoeba algorithm or whatever. It basically changes different variables and then finds out what the eventual best result is, which it found after several iterations somewhere around here, right? And then I actually manually stopped it. So you can also manually stop it. So you can say stop. So once once it goes to several iterations, you can manually stop it clicking this button, or you can even pause it. Okay. So once that is done, then what you do is it returns, once you stop it manually using that figure, then it'll return the optimum variables, which replaces this parameter x, right? And then I use those optimum results to run a simulation and save the final results to compare them. And that's what I showed you here. So these are the final results. And this was exactly what I had showed you earlier in the previous video when we set it up, how we got those exact results. So that's it. Hopefully that's clear on how to run this optimization. Start by first including the path in your environment variables. Then you set up some parameters, upper bound and lower bound. Then you run a seed simulation. You set up a function that can return a cost with each simulation. Then you set up an optimizer based on whichever is your favorite optimization algorithm. And then once it runs, you get an optimized list of variables that give you the best results that you asked for from the cost function. And then you can plot the final results. So that's pretty much it. So this is one way of designing, an antenna, for example, to get a certain matching bandwidth uh, that you like. Okay, with that, I'll end this video. I'll also leave some references in the description if you want to learn how to design, let's say use slot patch antenna using different approaches, but this is a good approach, I think, in HFSS to design antennas like this. It can also be used for the inductors and transformers that I spoke about. Okay, thank you.